Hello, and welcome back to the Apache Flink Learning Series. In today's talk, we'll be covering an overview of how we can write and create Apache Flink applications. So let's get started. Apache Flink has different programming APIs available to write and program streaming applications. Each APIs offer different levels of abstraction and different levels of complexity and flexibility. At the highest level of abstraction, we have Flink SQL. This is a declarative language that most are very familiar with. Streaming data is abstracted as continuously changing tables. With Flink SQL, you can perform standard transformations and perform joins and aggregations through group bys. It is the easiest API to start with, but it is also the least flexible. Because the SQL abstraction is so different from the actual way that streaming data is generated and processed, to which we don't have control on how the logical graph is going to be built. So we might hit some challenges along the way. Next, we have the Table API. There isn't much difference between SQL and the Table API, as they both make use of the same abstraction of tables. However, the Table API is a programmatic API that directly integrates with Java and Python code, allowing you to work with the data in a way that is more coupled with the programming language of your choosing, where you can still use joins, group bys, filters, among other transformations. It may be that these levels of abstraction are too simple for your streaming processing logic, in which you don't need to work with the events as a table, but actually as a stream of continuous records. Here is where we have the Data Stream API, in which you work with streams of events where you can perform transformations, aggregations, group bys. The Data Stream API maps events one-to-one with actually how Flink receives and processes the data. The code you write defines the operator, the logical graph, and the way that data flows across them. The Data Stream API still offers some powerful constructions and abstractions, like different types of windowing and first-class support for event-time semantics. And you can as well use its native transformation methods to build your own processing logic. But if we want to go deeper and the Data Stream API is not sufficient to tackle the complexity of your use case, you can go as deep at Flink internals with the process function. The process function gives you the finest grained control on processing of each single event and application state. It also allows you to implement custom time semantic using timers. For instance, trying to invoke a custom action whenever two records arrive with a 2-second difference, or if you want to build your own custom windowing logic. This is the most powerful API Flink offers, but also the most complex, as it gives us the highest level of control. It also gives the developer the responsibility of controlling precisely what the application is doing. In terms of programming languages, all programmatic APIs can be written in Java, or any JVM language like Kotlin or Scala. Or it can also be written in Python. SQL code can be sent directly to an Apache Flink cluster via dedicated interfaces, or it can also be embedded in any Java or Python application. But let's stop with the theory and let's take a look at some examples of each of the Apache Flink APIs. For all examples that we're going to be shown in the Flink Learning Series, we're going to be using IntelliJ as our IDE. It allows us to compile and run locally Apache Flink applications. Even though we're talking about SQL API, as you can see, the SQL is going to be embedded as part of the Java application. In order to start, we need to provide the stream execution environment, and from it, the table environment. This is where we're going to be executing our SQL logic. It's going to be providing that abstraction of tables. When we work with a Flink SQL application, we have three main components. We have a source table, we have a continuous query, and we have our sync table. For our tables, we need to define them and provide the schema beforehand. This means that if our schema evolves, we actually need to stop and update our application in order for it to be able to process. We also provide the connection configuration, the type of connector that we want to use, which in this case, we're going to be consuming data from an Amazon Kinesis data stream, and all the necessary configuration for it. Flink SQL provides some native transformations, such as filters, such as aggregations, but there might be some processing logic that it may not be part of the library. For them, you can then use user-defined functions, and you can then provide them as Java classes. So let's take a look at one. Here, we can use a Java library that allows us to calculate if a given coordinate is near one of the major airports, such as JFK, LGA, or EWR. Once that we have our functions and we have our source table, we're able to run our continuous query. We can provide those queries as views if we want to use that query as part of another query in our application. We're also able to run subqueries within one query by itself. So here we're creating a temporary view where we are applying those transformations and making sure that we do not have any events, that the airport code is null. And then we can use that first view as part of our next query, where we're doing an aggregation, counting how many trips per airport have happened in the last 10 seconds. Do bear in mind that as we're doing a window aggregation, we're not continuously counting all the events that are near an airport, but we're counting just by 10-second intervals. And lastly, we create our sync table or our destination. We also need to provide the schema and the configuration for the connector. Since we want to see this within the screen, we're just going to print. Once we have those three main components, it's time to tell from where to where we're going to be sending our data. So, since we have these views of our continuous transformations, we then say that we want to insert into our sync table the following query. And this following query, it's using as its source the final view that we created. We could be using the first table and have here a way more complicated query, but in this example, this is how we're doing. So if we execute, let's start our data generator. There we go. And after 10 seconds, we can see some results. But wait, we talked about table and abstractions. Why am I seeing individual events being printed in the screen? Well, same as when we submit a query to a database and the query planner builds the graph of builds the processing logic, Flink SQL does the same, that with the SQL code, it builds the application graph. It then generates the operators and the required state in order then that whenever we manipulate the data within Flink, it feels that as we're working with a table, but again, at its essence, are still streams of events. So when we want to output those results outside of Flink, we're going to be seeing streams of events as well. Now let's look at the table API. Same as before, as we're using an abstraction of tables, we are creating that table environment from the stream execution environment. And again, we have our source table, we have a sync table, and we're going to show the transformations that we can do along the way. But since we are working with that table abstraction, we again need to provide that schema before we compile. So we create that schema, but we're not now doing it using SQL. We're using Java objects and Java classes for it. We create a temporary table with that schema, and we define the connector and its configurations. And then we can apply the same kind of processing logic, but if you notice, it's more tied into the programming language of our choosing, which in this case is Java. We're still selecting columns, we're still applying filters, but we're applying it as methods to our Java objects. We apply the same transformation and aggregation per 10-second interval. We create the destination table where we're going to be printing those results, and we run an insert command in which we're inserting the trip count into our destination table. So let's execute this code as well. Again, we're seeing individual streams of events being printed. But now let's go at the data stream API. In the data stream API, we've mentioned this briefly, but everything that we write in the main class, it will be used to create the logical graph. So here we do have direct control on how the data is going to be flowing from one operator to another. For the data stream API, we just need to have the stream execution environment. We build the properties, so with all the necessary configuration for our connector, again, Kinesis data stream, and we build our data stream. We provide the Kinesis data stream name and how we're going to be deserializing those events. We will be able to use native deserialization provided for Kinesis so that we receive strings, or we can parse them directly into POJOs. So if I go, I can then see, I can add additional methods, and I pass the fields that this class, this Java object will have. I applied transformations. Then again, if you notice, here I'm not really defining or registering user-defined functions. I can use its native constructions such as flat map or map in order to build my processing logic. In SQL, if I needed to do an aggregation, I would use a group by. In the data stream API, we use a key by. The key by makes sure that all the elements that have the same key are routed to the same operator. And once we do that, we can apply our windowing logic and do our aggregations. Here we can see that there's already some abstraction in order to do that windowing, and where we're going to be doing that 10-second interval. And lastly, we apply our aggregation where we're going to be counting the number of trips. We define where we're going to be sending trip count, where we directly send to print. And we are going to now execute. And we're going to see our events after that 10-second window. This is a high-level explanation or example of the DataStream API, because in the next chapter, we're going to be covering it in detail. So stay tuned for the next session.